okay, for the given input, right? So now this is an example which we discussed in last class to convert from binary to decimal, right? So what we do over here is here we are taking the grammar as a right recursive grammar. Okay, as you can see in the second production, L gives BL or B. Okay, so over here, what we are doing is we are taking a right recursive grammar. Okay, so and if you look at the actions that we perform when a particular production, whenever we have a particular production, okay, you have seen that in the formula, okay, in the second production, okay, L gives B L1. Okay, why we are taking L1, also why we are taking L1 L2 in the first production. Okay, we have to understand over here that we are not considering L1 and L2, okay, they are not separate. Okay, they are simply L, but what we do is when we want to evaluate the attribute, okay, over here the attribute is CNT, okay, short for count, and val, short for value, right? So over here what we do is when we are evaluating the attribute, okay, we want to know that from left hand side we are taking the attribute to right, or the right side attribute is generated from left. Okay, that is also possible. So far all the examples that we have considered and few examples that we will consider today, okay, they are all having synthesized attributes, right? So we must be very clear that what is a synthesized attribute. From the name, okay, we can have an idea that synthesized means made from something, right? So when a parent's attribute is made from the child, okay, so whenever we are having any reduction, okay, at that time we are evaluating the um, attribute. So those attributes are called synthesized attributes, and here in the notation, if you want to write using notation, represent using notation, then we will write as of n, as of b, okay, meaning synthesized attribute of n, synthesized attribute of b, synthesized attribute of l, and so on. Okay, so over here in this example, all the attributes for all non-terminals are synthesized attributes, right? Now over here at the end, okay, the terminals are only two, okay, 0 and 1, because our binary number will contain only zeros and ones, right? Now same example we did with another grammar, okay, making a small change over here, okay, which I am calling second method, okay, just to separate it out, okay, it's just another grammar to do the same task, right? So over here we are using the left recursive grammar. As you can see over here in the second production, L gives L1B, okay. Now what I am doing over here is to simplify my task, okay, if you observe, I am taking a very easy formula, okay, to convert my binary value into decimal, okay, and same formula if we understand and remember, okay, similar formula, okay, with slight change can be used to convert octal to decimal, hexadecimal to decimal, okay. So any number system to decimal if you want to convert, okay, then this formula will be very helpful to us, okay. So over here what we are doing is, as I said that it is binary to decimal, so our terminal is having only two symbols, okay, either 0, it can be our terminal, or 1 can be our terminal, right? So now let's try to understand that how this same method can be used, okay, for conversion of octal to decimal. I hope that this grammar, okay, is clear to all of us, okay. When we are talking about synthesize, and when we are whenever we are talking about synthesize attributes, okay, we will always be following bottom up left to right approach, right, for evaluation. So uh, for this, both these grammars, okay, whether they are left recursive or right recursive, okay, for this both grammars we are getting correct evaluation of the attributes, means we are able to convert binary to decimal, okay. So now let us see that what changes do we make, okay, very small change if we make, then this same similar grammar can be used for converting octal to decimal. So let us see that. Now, if I want to convert from octal to decimal, just observe that there is only slight change. Okay, though the number of productions are increasing, but in general, if you look at the formula, okay, it is very easy to remember. Why so? Instead of 2, we are simply writing 8. Okay, because binary is of base 2, octal numbers are of base 8. So simply replace 2 with 8, right? And our our terminals will be either 0, 1, 2, 3, 4, 5, 6, 7, right? Because octal numbers can have any value, octal number can be formed from any number between 0 to 7. Okay, so just we make small changes in the grammar. Okay, we have a grammar that will convert octal number to decimal. Now you all know the technique of generating the parse tree, okay, from the given grammar, and then how you are supposed to go about the evaluation. All these attributes again are synthesized attributes, right? It is exactly the same as the previous case. The only thing over here is we have to increase the B20, B21, such productions we have to increase, and we have to change the base. Okay, because binary, now we are not working with binary, but we are working with octal. Okay, so same example can be transformed, okay, to do another task, that is octal to decimal. Any doubts so far? Okay, I hope that all of you know this formula, right? If you use this formula, then octal to decimal conversion is very simple. Same can be used in the grammar as it is shown over here. Okay, moving further, as I told you, similarly we can work with hexadecimal to decimal conversion also. All we do is instead of 8, okay, which we wrote, we are writing 16 because hexadecimal is of base 16, right? And we increase some production, right? Now over here, just for simplicity, what I have done is I am taking A to F, okay, which we use to write decimal numbers, okay, in lower case. Now, if you want to keep it in uppercase, then instead of B, which we are writing B production, okay, B20, B21, and so on. The B non-terminal, why we are taking? Because we just want to represent a bit, okay. But now instead of that, you can just write some other symbol so that there is no conflict in rule number 15 over here, B to B. Okay, just for the sake of simplicity, I have written over here in lowercase. Okay, if you want to write it in uppercase, then you have to write it accordingly. Okay, but don't give same symbol. You should not be using the same symbol. Okay, of uppercase and lowercase. Okay, same symbol you should not use. Okay, if you do so, then it will lead to a lot of confusion. Right. Also, most of the times we are writing non-terminals in lowercase. Okay, so that also satisfy over here by writing A to F in lowercase, right? So the still the number will remain same. It is just what we write and try to understand. Okay, so basically point of adding this slide into the presentation is you should be able to convert hexadecimal to decimal also using SDT. SDT is already given to you in the slide, right? So for any given input, okay, you should be able to generate parse tree, trace it, okay, and generate the output. Any doubts so far? Right? So if you use the first method, then it is not that easy, okay, to change it to octal to decimal and hexadecimal to decimal. But the second technique, okay, makes your task quite simple, right? So I would advise that you use this second grammar, which is left recursive, okay, for your example. But if you are doing it with the other one, okay, then also it is fine, no problem. Okay. And this is to again emphasize the fact that same task can be done using different grammars, okay, and they also can be correct. So the only way to check is that you give an input and if it generates an expected output to you, okay, for typical cases, okay, then it means that your grammar is okay. Fine. Otherwise, it will not give you correct answer. Right. So this you should keep in mind. Right. So with an assumption that whatever you have missed, okay, people who are not present in the last class, whatever you have missed, okay, that is now covered, right? Because this is as far as examination is concerned, okay, frequently questions related to this conversion, okay, ability to write conversion from one number system to another one is asked, okay, either binary to decimal, octal to decimal, or hexadecimal to decimal. Okay, so now as we are nearing the end of our teaching session, okay, we need to focus on how to score, okay, by preparing in a crisp manner. Okay, so this you can take it as a hint, fine, right? So far the examples that we have considered are first we have taken a simple grammar, okay, that generates or rather that accepts, not generates, I should say, that accepts strings, okay, in which number of A's, B's and C's are equal. Then we have also seen binary to decimal, octal to decimal and hexadecimal to decimal. Okay, such examples we have seen. Then next example we saw was a simple calculator in which we took two operators, multiplication and addition, right? And we computed the output, okay, for the given expression. Then we also saw how we can convert from infix to postfix, again using the same grammar but slightly different semantic rules. Again over here, if you are able to if you are able to write an SDT, okay, slightly different than what I am discussing over here, if it gives you the same answer, okay, if it gives you the correct answer, then it is considered as valid. Okay. Now, regarding the simple calculator, okay, if you want to add the functionality of subtraction and if you want to add functionality of division, okay, then its behavior is quite same as addition and multiplication. Okay, so that is why the grammar that we have been considering in all the examples, okay, that you have studied so far, we are simply taking addition and multiplication. Okay. Now, what I'm going to do is, I'm going to show you another grammar, okay, and with the help of which we will generate an SDT for desktop calculator, okay. In the last class, there was a question that if we want to use power, okay, if you want to use the caret symbol, if you want to go for x raised to y type of evaluation, okay, then what we should do. So if you want to add that operator into your grammar, okay, then you can add it somewhat like this, right? So the first four productions, okay, they are as we have learned previously, okay, and you have used it many times. Now what I'm doing is over here, focus on this one, this f gives x raised to f. Okay. Now, why have I written this production in this manner only? Last time when the question was asked, I told you that you will have to write a different grammar, right? So here is the different grammar. I don't know who asked the doubt, okay, last time, but I think it might have occurred to many of you. Okay. So what we are doing over here is now we are using this grammar. Now, if you look at this production, yes, because it is right to left evaluation of power, correct. I think probably he will only ask this doubt last time. Okay, I'm not sure, but rest of you, okay, this is very important. Okay, this you can use in other examples also. Also, same concept, okay, will be helpful to you whenever you are having any operator which does not have left to right associativity but it has got a right to left associativity. If that is the case, then what you have to do, you have to represent it likewise in your grammar. Okay, getting this, right? In one more example which I'm going to discuss in today's lecture or maybe tomorrow, I'm not sure in which lecture we'll be able to cover that example, right? We will be using equal to sign, right? So assignment operator is also having an associativity from right to left. Okay. Now for this grammar, one more thing you should observe is that when I add a symbol, okay, when I want to add an operation, its production's position is very important in the grammar, right? First we are we are writing a production, okay, for plus, then we are writing for multiplication, then we are writing for caret sign. Why we are doing something like this is because of the precedence. So whenever we are writing a grammar, okay, associativity is important. Also, the precedence is important. Now, of these three operators, addition, multiplication, and power, okay, which one has got the most, or rather, which has got the highest precedence? Okay, the operator which you must evaluate first, and that is caret, right? So it will go below, right? The ones which is having the least precedence, okay, that we will take first in writing the grammar. As far as evaluation is concerned, okay, it will follow the same order as we are doing in maths. Okay, we are not changing any rules of arithmetic. Okay, but your grammar, okay, should also satisfy those rules. Following this, okay. So I hope that this grammar is clear to everybody, right? And now I'm going to show you a few examples, okay, to justify this fact that this grammar, by changing its recursiveness from left, which we are usually taking for left associative, now this is right associative, so we are making it right recursive. Okay, so we are going to take a few examples, right, and then you can try for your own also. Okay, this is again very important. Okay, some examples based on this SCT can also be asked. Okay, so now what we are doing is I'm just adding some actions, right, that I'm going to perform. Action will be very simple for a desktop calculator. Whatever is the symbol, that operation you have to perform, right? Now, here also one more thing which everybody should understand is that whenever we are writing a grammar, it is simply symbols, right? Now we are giving some meaning to those symbols by writing the semantic rules or semantic actions which need to be performed when we have a certain production. Okay. So if we are having an input 2 plus 3 into 4, which we have taken previously, where we did not have the caret symbol in our grammar, we did not have that production. Okay. So now, if I use this particular grammar for the same input, then my parse tree generated will be as you can see on your screen. Okay. So now, what is the difference? The parse tree is having a slight change where over here from T we are deriving F, from F we are deriving X, and from X we are having the number, right? So F to X, X to number, F to X, X to number, instead of the previous case where we were having F to number. Okay, so that is the only difference, okay, that will happen because of this production. Okay, production number 6. Okay. So because we have added these two, production number 5 and 6 has been added now. Okay, so that is why there will be a change in our part. As such, it is very simple to understand. Okay. Now what we are doing is I want to give an emphasis on using the power. Okay. So now if my input is something like this, 2 plus 3 raised to 4. Right. Then can you generate the parse tree for the given grammar? Now grammar is with you, right? What will be the parse tree for this particular input? Can you try it out? Okay. Take 1 or 2 minutes. Okay. I'm sure that 2 minutes is very enough. Okay. To generate the parse tree, right? What you have to be careful about is you know this very well. You have taken a lot of examples, right? So you start from E, right? Now over here, I have separated out the left hand side and right hand side of the production, okay, by taking suffix 1 for the right hand side non-terminals, okay. So over here, if you see, okay, how our tree will be generated the same way, okay. You start with E as your root symbol, okay, and then your tree will be generated, okay. So let us see that what our tree will look like, okay, after 1 minute, after you have done it in your notebook, okay, then we will see. So now for this particular input, 2 plus, see over here you can see 2 plus 3 raised to 4. Now when can I say that this grammar and the parse tree which I have generated with it is correct? When can I say it? When it gives me correct output. Okay. So what will be the output of this particular expression? 2 plus 3 raised to 4. But what will be my output? Whatever is output, okay, that must be generated by evaluating this input using the SDT. Okay, so let's check it out. Okay, whether our grammar and the passkey that we have generated is correct or not. Okay, so how are we going to start with? Because the attributes over here are all synthesized attributes. Now you observe over here that what are the attributes? For E, we are having value. For T, we are having value. For F, we are having value attribute. Right? For X also, we are having value attribute. And for num, now what is num? Num is my terminal. So for terminal, we have already discussed that terminals have synthesized attributes which are lexically provided. Okay, so they are lexically synthesized. So those are also considered as synthesized attributes, but its value is given by our lex. Okay, so now let's see. We have to remember our rule. Very simple. We have to start from bottom up, left to right. Okay, so let's start it. First and foremost, we start with bottom left. Okay, bottom left num. Now what we do is we have to check whether num is in any production on the right hand side. Yes, we have, right? So you know this technique very well. Okay, emphasis is given to the technique is so that you remember this very well. Okay, so now num on the right hand side we find in the last production. Okay, x gives number. So number is reduced to x. So now what happens is using that production and the semantic rule or the action that is associated, x dot value equals to 2. Now x reduces to f. X reduces to f. So f dot value equals to 2. Next step. And correspondingly, what action we have taken, because of that f dot value became true. It is also highlighted on your slide, so you can get it very easily. Next, f is reduced to t, so t dot value equals to 2. Next, what happens is again we are moving from top to bottom. Sorry, from bottom up. We are using bottom up technique, right? So e dot value equals to 2, right? So what next? Now we have to move towards right. Okay, left to right also we have to move, right? So next symbol is plus. We don't do anything for it. Okay, now next is num3. So when we have this, okay, what is the meaning of it? Okay, that now num dot lex value equals to 3. And we have to see that whether num is in the right hand side of any production. Yes, it is. Okay, so num is reduced to x. X dot value equals to 3, right? So now again tracing our pass tree. Next, we will check for this one. It is just a symbol. Okay, it is not forming any right hand side of any production. Okay, so far, right? Okay, so what we are doing is next. Let us take next symbol. Okay, over here num4. So what happens is num dot next value equals to 4, right? Then num is reduced to x. So num is reduced to x. X dot value equals to 4. Next, what we do is x is reduced to f. F dot value equals to 4, as you can see on your slide, right? Now, what is the next step? Now comes the part where actually we are going to do some operation, okay? Because what we have is now our production is, we have to sort in our production, any of the production on the right hand side, whether we are having x caret f. Yes, we have one, right? So the one that is highlighted in your left hand side of your screen where we have written the SDT. Okay, so uh, we have to perform the action of f dot value equals to x dot value caret f1 dot value. So what is x dot value? It is 3. What is f1 dot value? Okay, so here if we know that f1 is the right hand side f, okay, then it is not having any confusion. So f dot value equals to 4, right? So 3 raised to 4, okay, gives us 81, right? Now moving further, f is reduced to t, right? So t dot value equals to 81. And finally, now what production we have to check? E plus t. Do we have E plus T anywhere? Yes, we have. Okay, we have a production, right? So E plus T reduces to E. E plus T reduces to E, and what action we have to perform? E1 dot value plus T dot value. Okay, there is a small mistake in the slide. Okay, I will just change the semantic rules that I was supposed to highlight, right? But basically, okay, just understand that E dot value equals to 81. How did we get it? From 2 plus 81 gives us 83, right? So output 83 is now generated. Getting this one? Okay. So now it did not go for 2 plus 3, 5 raised to 4. Okay, it would have been incorrect, right? And that is why we need to make use of this particular grammar. Let us take one more example, okay, that we will take slightly quickly, okay, so that you are able to thoroughly understand this particular grammar, okay. Now for this particular input, 2 raised to 3 raised to 2. Now see, when we are given some input like this, okay, now we are talking about a new input, okay, the previous example is already over, right? So now if we are taking this particular input, then in which order I should perform the operation? Whether I should go for 2 raised to 3, that is 8 raised to 2, 64, or I must go for 3 raised to 2, that is 9, and 2 raised to 9, that is 512, yes, 512, right? So should I go for something like this? If I am providing parentheses, then there is no doubt, okay. Otherwise, if we are not having any parentheses, okay, then whatever is the default precedence of the operators and its associativity will apply, okay. That is a simple rule of arithmetic, right? So now what we need to do over here is, for this particular example, let us generate the parse tree. Okay, now I'm going to show you the parse tree. Please try to understand it. Okay, that how we are getting all the productions. E gives T, T gives F, F gives X caret F. Okay, then from X we are having num, and then have F gives X caret F. Okay, the first X is num. Okay, it gives num, F gives X, and X gives num. Okay, so this is how we will have our parse tree for this particular input. Okay, so now over here, okay, the right recursive production will play a lot of role. Okay, now previously, okay, if you feel that if I take though the associativity is right to left, okay, I don't take right recursive production, but I take a left one. Okay, then in the previous example it wouldn't matter much, okay, you probably will get the same answer. But for this example, okay, like I told you that if you take a left recursive production in production number 5, okay, F gives X caret F. Instead of that, if you write F gives F caret X, okay, then what happens is it will compute 2 raised to 3 first, okay, it will give you 8 raised to 2, finally answer 64, which is not correct, okay, which you can check, right? So that is why this is very, very important. Okay, so now let's take the trace very quickly. Okay, num reduce to x dot value equals to 2, right? Then we move again bottom to up, okay, so num reduce to x, right? Then again next, whenever we are having symbol, I am sure everybody is having no doubt that we don't have to do anything, okay, it is just pushed onto the stack, okay. When it is pushed onto the stack, okay, it will wait till a production, okay, whose right hand side match is, okay, is available to us, okay. So when we have that handle, okay, I think it is called handle, right? So whenever we have it, okay, only at that time we do a reduction and then the action is performed, okay, the semantic action or semantic rule that we have written, okay. So now num reduces to x reduces to f, okay. So now over here, now what production we have to check? On the right hand side of the production, do we have x caret f? Yes, we have one production like that, right? 3 raised to 2 we are supposed to calculate, okay. So 3 raised to 2, Okay, 3 power 2 is 9. Now what is next thing that we need to do? Okay, now what will be reduced? X carat f will reduce to f. X carat f will reduce to f again. Okay, same operation. So what we have to do? 2 raised to 9, right? Because now value of x, okay, that we are reducing at that time, the value of x is 2 and value of f is 9. Okay, so 2 raised to 9 is 512, right? Now moving further, okay, f is reduced to t dot value equals to 512, and finally e dot value equals to 512, right? And our um, output 512 is generated. Okay, clear to all of you, right? This is a new grammar, maybe you have not used it, I'm not sure. Okay, that is why I just took these examples, okay, so that it is of no doubt to anybody, right? So now please be sure that if you are asked, okay, to generate a grammar, okay, and then finally the SDT for a desktop calculator given the functionalities, okay, if you are writing a plus, minus, multiplication, division, caret, okay, if everything is given to you, you should be able to write a grammar, okay. It will have more productions, no problem, right? But you should be able to write it, you should be able to write the semantic rules, right? So similarly, you should be able to use this particular grammar, making changes in your semantic rules for infix to postfix. Okay, that also you should be able to do. Okay, that example I have not included in the slide, but I am sure that with these two examples, all your doubts are very clear. Okay, so what happens when the associativity is not left to right, but it is right to left? Okay, clear to everybody? Any doubt? Okay, this is very important to understand, right? So whenever we are writing a program, we are not concerned much. But now this is a subject of compiler. Okay, so we have to give emphasis and focus on all these small things. Okay, they matter a lot, right? So in last lecture, actually, we were supposed to start working on SDT to build a syntax tree, but I realized that in previous topics I did not include those. Uh, Details regarding binary to decimal second technique, okay, how it can be extended to octal to decimal and hexadecimal to decimal. Okay, so I just included those topics, okay, in today's lecture, right? And these example, okay, using one more operator, I thought that that was also important, okay, as we were discussing calculator and infix to postfix. Okay, along with that, you should have an idea of those associativity related operators. Okay, so now we are going to discuss the SDT to build the syntax tree. Okay, so this is how the syntax tree will look like for this particular input, right? So now I hope you know that syntax tree for this input, okay, how it is generated, okay. I'm sure all of you know it, right? Now our aim over here will be to write an SDT that will generate an output like this. So it will generate a tree structure for us, okay. So tree structure means what? We have to generate a few nodes, right? And then we have to also specify whether it is a left child or right child of its parent, right? So for a tree, you all know very well that the leaf nodes, okay, will not have any pointers, okay, or rather the pointer value will be null. And for rest of the nodes, okay, you have two pointers over here because this is a binary tree, right? So we will have one left pointer and one right pointer, okay. So whenever we are generating a new node, okay, we have to check that whether it is a number or it is a symbol, okay, and accordingly we have to decide where it is to be placed in the tree, right, and what we are supposed to give values to its pointer, okay. So let us see this SDT and try to understand it, okay. For this particular input, okay, the parse tree will be the same, right? Here I have used a simple grammar, okay, not the modified one that we discussed in today's lecture, okay, because the operators that we are working with is only plus and multiplication, okay. Now let us try to understand the semantic rules or the actions that we will perform, okay, when a
particular production. Okay, so now what we are doing is, whenever we are having a number, right, whenever we have a number, that will be a new node. Okay, so now what we are doing is, whenever there is a reduction from num to f, or simple terms for the production f gives number, what we are doing is, we will take a pointer. Okay, so basically f dot n pointer is pointer to the node. Means, what is the meaning of pointer to the node? Means we are storing the address of the node. Now why do we need to maintain the address? Because for other nodes, okay, if the link is to be made between right pointer to that particular node, okay, then we will require the address, right? It is very elementary. So what we are doing is, we are saving the address in of the newly created node. Mk node means we are creating a new node with left and right pointers as null, and the data portion, okay, of the node, right, it is containing the id name, or over here we will simply write down whatever is our number. Okay, 2, 3, 4, and so on. Fine. Okay, so here I can also write down num dot lex value, then also it is fine. Okay, here I'm not taking id over here, I'm taking num, so I should actually write down num dot lex value. Okay, well, this is just a notation. Okay, so there is a specific meaning to every terminal and non-terminal that are conventionally used. Okay, so this is still fine, we have understood the meaning, right? Now what is next thing to do? Okay, now when we are reducing from f to t, whenever we are having a production t to f, then what we have to do, simply take the pointer, assign the value of pointer value of f dot nptr. Okay, we are just giving its value to t dot nptr. Okay, now, whenever we are having a multiplication sign, what we have to do? That is also a node, right? The operator also will be represented as one of the node in the syntax tree, right? So what we do is, we make a node. Now, what we do with this node? Okay, t dot nptr into f dot nptr. Okay, so if that is the case, left pointer will be t dot nptr, right pointer will be f dot nptr. Okay, and in the data area of the node, okay, we'll put multiplication. Now, if you are having a production t, e gives t, then e dot nptr gives t dot nptr. Okay, this is very easy to understand. Okay, we are simply copying the pointer value from child to parent. Okay, from t, we are copying the value to parent. So again, over here, it is a nptr, the attribute is a synthesized attribute. Okay, I have not specifically given a dot s, sorry, synthesized attribute of E, synthesized attribute of T, synthesized attribute of F. Okay, that I've not described, but I think it is now very clear to all of you. Okay, and finally the first production, which we are considering last. Okay, to understand, we always go from bottom up. Okay, over here to understand. So E dot nptr equals to, we make a new node, and what will be the left pointer? E dot nptr. Okay, so now over here, E dot nptr means, actually we are talking about E1 dot nptr, and this is T dot nptr over here. Okay, so now let's take the trace very quickly for this particular input, and verify that the tree, like this, okay, as we have discussed in this particular slide, are we getting an output with the help of the SDT that we have generated? Okay, let's take it. So trace is very simple. Okay, we are having num. Num reduces to f. So now what we are supposed to do? We will make a new node. Okay, you can see on your slide, we have made a new node. Okay, left and right pointers are null. In the data area, we have put the ID name, or lex value of the number. Okay, let's just simply call it 2. And it is stored at location 100. That we are assuming. Okay, we are just assuming as of now. Actually, whenever a syntax tree is built, okay, for whatever symbols we have, right, it will be stored at some location, right? So let's take the location is, say, suppose at memory 100. Okay, so fptr equals to 100, right? Now next, f is reduced to t, so what we have to do is simply copy the value of f.nptr to t.nptr. Okay, node pointer we are simply copying. Okay, t is reduced to e. Again, same thing. We are just copying the value, right? Then next, okay, from plus we just move down and num value is 3. Okay, now what we do is, now what we have to do, when num is reduced to f, okay, what we are doing is we are making a new node. Okay, let's just assume that it is made at location 200. Okay, the node's left and right pointer will be null. Okay, as such we need it to be null because it is going to be my it is going to be my leaf node, right? Now f reduces to t, so nothing much to do, only just copy the value, right? Now num reduces to f. Over here you can see, right, that we are creating a new node. Simplicity, okay, wise, we are just putting that node at location number 300. Okay, address is 300, right? And in data area we are putting 4. Left and right pointers are null. Okay, now this is very significant. T.nptr equals to 400. Why? Because we have to create a new node. Okay, and what will be the left and right pointers? It will be t.nptr, that is 200. Okay, so in the diagram, okay, where we are developing the syntax tree, you can see that there is a link between uh, 200 and 400. Okay, so left hand side pointer of the node at location 400 is now pointing to 200, and the right pointer is pointing to 300. Say this information, how did we generate? Okay, we had it all in the attributes of our tree, right? So we had it in the attributes, right? And we were able to generate so far our syntax tree, right? Now next and final step will generate the last node, okay, that is at location 500. Its data will be plus, and left and right pointers will be from E and T respectively. Okay, so value 100 and 400. Clear to all of you? Okay, so now we can say that this SDT is correct. Okay, the sparse tree which we generated for our input is also correct. Okay, and what we are doing is we are generating the syntax. Now this example we have taken only 2 operators. Again you can expand this according to your need. Actual syntax tree building, okay, requires all the operators, okay, which are available, right? So in that case it will be, the grammar and semantic rules will be slightly different, okay, but it will follow the same pattern. So if given a change, okay, you should be able to work with it very easily. So this is how what we did is we generated the syntax tree. Any doubts so far? Anybody? Okay.
Fine. So let me take one more example. Okay, before we end the lecture, right? We still have 15 more minutes. So I think one more example will be able to trace. Right. Further, whatever is remaining, we will discuss tomorrow. Right. Now, before I start this example to discuss the SDT to generate 3 address code, I would like to mention that if there is any topic, okay, because most probably the lecture I am going to take tomorrow will be the last unless we have any new schedule. Okay, so what I would want you to tell me by end of this lecture in next 15 minutes while we are discussing this, also think about if you need repetition of any topic, okay, that I can accommodate it in tomorrow's lecture, or if you want to revise something, right? uh, that also you can let me know by end of today. Okay, by afternoon if you let me know, okay, then I can include it in tomorrow's lecture. Otherwise, I'll be discussing some examples, okay, and revising the topics, okay, which I think that are important. Okay, so we have a scope, right? We will be able to finish the syllabus as decided by half of tomorrow's lecture, right? So we will have time if you want me to discuss any topic or any example in particular. If you want me to repeat, okay, we will not be adding new content, okay, otherwise it will be a too much of the syllabus for you. Okay, so new things we will not add, only whatever we have discussed. If you need some repetition, please let me know. Fine. Okay, so now we are going to discuss the SDT to generate the 3 address code, right? So now what is 3 address code? We all know that it is an intermediate representation of our source program statement. Okay. So now what we are going to do is, okay, now just simply understand this one first, then we will go back to the slide, right? So if we are having our input like this, x equals to a plus b into c. Okay, this is my expression. Now if I want to convert my expression into 3 address code, okay, then I have also shown you the 3 address code. Okay, so the 3 address code will be generated like this, right? B into c first computed and stored into t1, then a plus t1 we will store it into t2, and what we will do is t2's value we will take back to x. Okay, because the answer of a plus b into c we need to store into x. So again over here you can see, as I was saying, that the assignment operator will have the least precedence. Okay, so it will be on the top. Because it has got least precedence, it will be on the top. Okay, so again in this particular example, if you are asked to incorporate some more operators, okay, you should be able to do it. Okay, pattern will remain the same, right? And I think all of you have also done a program in your lab session where you were supposed to generate 3 address code. Okay, the quadruple table, right? So understanding this will be very easy for you, right? So let us discuss the SDT. Okay. Now, what this SDT is doing, first and foremost, we start with S. Okay, our statement. Okay, and E equals to ID equals to E. Now, what action we are supposed to do? We are calling a gen function. Okay, this is all informal notation. Okay, so you can give any name of your choice. Okay, so what we are doing is we are generating a statement in the 3 address code, and what statement we are generating? Id dot name equals to E dot place. Okay, so now let us understand that what is this E dot place, right? It place is an attribute, name is an attribute of ID. Okay, so now um, okay, now let's take the next production. E gives E1 plus T, right? So now what we are doing over here when we have this production, it means what we are supposed to do is we have to generate a new temporary, right? So E dot place equals to, we will place a new temporary, right? And then what we will do is we will generate a statement in 3 address code. Okay, we will add it into our 3 address code in this particular manner. E dot place, okay, whatever is the value, okay, and what will it be? It will be the new temporary that we have made, right? Equals to E1 dot place, okay, so whatever is E1 dot place plus T dot place, right? So when we will trace our parse tree for our input, okay, then this will be very clear to you. Okay, if it is slightly confusing at this stage, okay, don't worry about it, right? Now E gives T, what we are doing is simply copying T dot place to E dot place, right? Now whenever we are having multiplication, T1 into F is my right hand side of the production, then what am I supposed to do? Basically, whenever I have a new operator, whether it is multiplication, addition or assignment, what I am supposed to do is I will generate a new temporary. Okay. If it is assignment, then simply we will just assign. Okay, so not in that case, sorry. But plus and multiplication, and if extending it to subtraction and division and so on. Okay, what I'm going to do is I will generate a new temporary, right, and then generate an entry in the 3 address code. Generate a statement in 3 address code. Okay. Now T giving F, simply copy F dot place to T dot place. Okay, and if F gives ID is my production, then F dot place equals to my ID name. So what I'm going to do is I'm going to place the name of the ID, okay, as an attribute of F. Okay, right. So basically the place attribute of E, T and F will contain the name of the ID. Okay, following this, right? So now let's take the example. We will be taking this same example. We will check whether from the input we are able to generate this particular 3 address code or not with the help of the SDT that we have written. Okay, right. So this is how we are going to start. First and foremost, for this particular input, this will be my parse tree. Okay. This is slightly new. I'm not sure whether you have done examples of grammar having assignment operator. Okay, so I'm just showing you the parse tree. The parse tree will look like this. Okay, please try to trace out for this given input. Okay, ID is my x. Okay, on the left it is equal to, let's just trace it, x equals to a plus b into c. Following this, okay. One more thing, for those who are not able to be sure that whether the parse tree they have generated is correct or not, all you should do is take all the leaf nodes on one level. Okay, when we are drawing here, what we are doing is I have just shown the levels at by writing them lower to the previous level. Okay, but if you write all your leaf nodes on the bottom of your page, okay, and if you are going to see your input, okay, it means that your parse tree is correct. Okay, provided you have used all the correct production. Okay, that is naturally the case, right? But then it means that you have not missed out any symbol from your input. Okay, you can check likewise. Okay, so this is just a small informal hint. Okay, it's not the actual way you do it, but this is just for verification. Okay, informal verification whether we have done it correctly or not. Okay, now let's start. Okay, one more thing. We should check, okay, that what type of tracing we are supposed to do. Okay, now this attribute, okay, whether it is synthesized attribute or not, how we will check? If we are taking the attribute value from child to parent, okay, so with each reduction the value propagates on the top to the parent. Okay, it means that it is a synthesized attribute. Your place attribute is a synthesized attribute. Okay, another name given to the SDT, okay, is synthesized SDT, or we also call it SSD also it is called. Okay, synthesized definition, right? So that is just the name. Okay, now let's look at the trace, right? ID X, ID A, ID B, ID C. Okay, we have just put all the values. So now the input is very clear from our parse tree, right? Now let's take the trace ID. We start from bottom left. We start from bottom left because it is synthesized attribute. So now ID then equal to, okay, nothing much to do so far. Okay, because ID equal to is not present in any of the right hand side of the product. So now ID A. Okay, also I am highlighting for this particular example that how our input is getting passed. Okay, so X equals to A, then ID is reduced to F, so F dot place equals to A, right? Then we have F is reduced to T, so T dot place equals to A, right? Then T is reduced to E, so what happens over here? E dot place equals to A, right? Now next symbol is plus, right? Next ID B, okay, so ID dot name will be now B, right? That is like given lexically, right? ID reduces to F, so F dot place equals to B, then F reduces to T, so T dot place equals to B, right? Now multiplication, okay, so nothing much to do so far because now what we will have on the top of the stack, T and into. Okay, so T and into is not there in any production, right hand side of any production. Okay, so it will still remain on the stack, right? Then we have ID C, so ID dot name equals to C will be given lexically, right? And ID is reduced to F, so F dot place equals to C, right? Now on the top of the stack we have T into F, right? So T into F is reduced to T. Do we have such a production? Yes, we do, right? So now what we do is we create a new temporary, give its value to t dot place. So t1 we have given, right? And now t1 equals to what we are supposed to do, just what we generate as an entry in our 3 address code. T1 equals to b into c. So how did we get b into c? T dot place is equals to b into f dot place equals to c. We got those values from there, right? And we generated this entry in our 3 address. I hope it is clear to all of you. Okay. Now moving further. Now what we have on our stack is, okay, E plus T. Do we have any such production? Yes, we do. Okay. So now what to do? E dot place equals to T2. Okay, sorry, I have just not been able to highlight it in this slide. There is a small mistake, okay, as far as presentation is concerned. Okay, but please try to understand that we are now looking at the second production. Okay, so we have created a new temporary E dot place equals to T2. Okay, and we are generating an entry in our 3 address code as T2 equals to A plus T1. I hope you are following this. Okay, I have not been able to highlight it, but I hope that you understand that what is going on. Okay, and now finally, okay, when we have our symbol S, okay, what is it we are supposed to do? Okay, ID equals to E is reduced to S. So the action that we are taking is we generate ID dot name, that is X, equals to E dot place, which is equal to T2. So sorry, X equals to T2. So finally, okay, we have reached the root and we have generated the 3 address code for our input. Okay. So we have a few more examples to discuss, but I'm not going to discuss that example today. Okay, we will discuss it tomorrow, right? So we still have 2 more minutes. Okay, till it is 11. So if you are having any doubt in any topic, okay, or you need any explanation in any of the examples, okay, a repetition of it, right? Then please let me. Okay, so I'm going to stop the presentation right now, right? And you still have a minute, okay, to just let me know if you need some help in any of the topics, okay, covered so far, right? Otherwise, whatever I feel important, okay, that I'll be discussing in tomorrow's lecture. Okay. So while the lecture is going on tomorrow, okay, if you come up with some doubts, okay, we will open the previously discussed presentations, okay, the PPTs which I've already shared with you that we can refer, and then I can explain it to you again, okay, if you are having any doubt. Okay, if we have time after discussion from my okay, attribute grammar, okay, sure. Introduction to attribute grammar that I will start with in tomorrow's class. Okay, sure, I'll do that. Anything else? Okay, it is 11, so I am ending the meeting from my side. Okay, if you have any topics, okay, which you really want that I should explain it to you tomorrow, okay, then you can just drop an email, okay, as early as you can, right? So I can just prepare some material which I can share with you. Okay, so I am ending the meeting from
Good morning, all. Okay, so first thing first, today at 3:30 we'll have a laboratory of ML, and CC lab will be on tomorrow 3:30, right? So make sure that today at 3:30 we'll have ML lab. Fine. And in as we have discussed in last session, today we'll discuss encoder decoder architecture, which is not in your syllabus, but from practical perspective, or let's say from the industry perspective, that is very important architecture, and we'll try to have some intuition or look at that particular architecture, how you can design the encoder decoder, right? And if you consider the transformer which are actually based on this encoder decoder. Fine, so let's begin. Okay, so look at this diagram, and which architecture that is, which deep neural network architecture it is, whether it's CNN or RNN. Can you identify that by looking at the figure? That's the recurrent neural network, right? Because we have this recurrent connection. Fine. And in one of the laboratory, we have this intuition of recurrent neural network RNN. Right, so there might be many application of this RNN. One is mentioned over here. Let's say we need to predict the next word based on the given words. Fine. So let's say whenever the starting statement is there, so this is go is a starting label or the starting statement. Whenever that particular label is there, we are supposed to predict I. Whenever we have this go and I, we are supposed to predict M, and so on. Fine. So this is one basic application where we are supposed to predict the next word based on the previous words. Fine. And I'm not going in detail of this RNN architecture once again, but uh, we are aware about this architecture, right? And what should be the model, what should be parameter, loss function, and so on. So we have discussed this in the laboratory. And now if you think about some input, let's say the output is a softmax. So we know that out of these 5 values, and we're assuming that they are I am at home today. These 5 words are only there in our dictionary. So we have these 5 values. Out of that, this particular value is 1. Right? Rest are 0. Right? Based on the highest probability value of that particular name. Fine. So now we'll feed that input. So that is 00100. Fine. Where this 1 is related to what? Right. So once you feed that, the next output that you get is, let's say, 00010, and now we'll feed it to the next input. Fine. And so on. So once you provide some input, lateral, this architecture can generate the next word. or you can say if you continue with that process, it can generate the paragraph. And so there are many application of this particular situation or this scenario in real world. One that I can identify is the fake news generation. And you might have heard about that social media is popularly or widely used in the election, specifically for American or any for any country, right? So the election parties are using that social media frequently. So one thing is, let's say if I consider a particular party, so what you need to do, you need to generate some data or different news related to the party or political leader, which can you can say a positive sentiment news. And so one way is you can hire some good writer who can write different articles for that purpose. Another way is, if you have this kind of architecture, just feed some initial line to that architecture and the architecture will generate the rest of the paragraph. And so if you even if you search on the net, you may find some model which actually perform this task, right? And specifically if you try to see some demo of GPT-3, it is available, the statement generation, where you just need to feed initial statement, and based on that initial statement it will try to complete that particular statement as well as it generate a full paragraph or maybe more than that, right? But let's consider the other example where we have this particular picture, and for that picture we want to generate the text, right? Or you can say for that particular picture we want to generate the caption. Fine. So if you consider this picture, which architecture will use to deal with images? In general, which architecture will use to deal with the images? Right, the convolution operation you need to apply, or in general you can say you are supposed to use CNN. Fine. Now to generate the text from an image, you need the text is a sequence based data, right? Where there in the case of image there are no such sequences. If it is a video, then the scenario is different. So to generate that sequence where individual word is actually dependent on the previous word sequence, you need to deal with the RNN architecture. So that means in specifically in this application or in this example, you need a combination of both, that is CNN as well as RNN. So on that idea, this encoder decoder model is designed. So what you can do, let's say you have this input image, you just have this input image, nothing else. You are going to feed that input image to the CNN and assume that we have already trained the CNN on different images. Fine. And we'll able to generate some output. Let's say that is this output S0. Fine. And this FC7 just indicates it is fetched, this output is retrieved from the 7th layer, or specifically 7th fully connected layer. And if you can recall, in the case of CNN we have three kind of layers: fully connected, convolution, and the pooling layer. Fine. So the output at FC7, that is, let's say, indicated by this particular blue cell. Fine. And assume that you have one another RNN architecture ready with you, which can able to generate the text. Fine. So if you just feed some input or some data, it will able to generate the rest of the data. Fine. So we have these two different model trained on the different data, and now our goal is to connect these two models. Are you getting the problem statement, what we are supposed to do? One more thing that you need to observe is, in the training of this CNN, there is no role of this text data. We haven't provided any of this input, the text input. And similarly, for this text data, we are not providing any input related to this image. Fine. So let me repeat. So we have two different model. One is the CNN. So this you can say one single model. And the rest part of this particular figure is the RNN model. Fine. So we'll train the CNN on different images, and similarly we'll train this particular RNN model on different text data. Right, and the goal of this RNN model is to generate the next image, next text data. Right. So now our application or our requirement, that is to generate the caption for this particular image, we need to somehow combine these two value, the output of CNN as well as there should be some connection between the output of CNN and this particular RNN model. So there are many ways to connect to make this connection. Specifically, let's see two different approaches. The first approach is this FC7 output, and what do we mean by FC7? Once again, that is fully connected seventh layer, right? And if you can recall the convolution neural network, this FC layer are generally at the end in the CNN. Fine. We'll start with the combination of pooling and the convolution operation, and we have many such combinations, and at the end we have FC layers. Fine. So from one of the CNN architecture, let's say from the FC7, whatever is the vector that we are able to retrieve from the FC7, we'll feed it to this RNN network as S0. So if you can recall that RNN slide, whenever we start the computation, so this is your S1, this is S2, S3. How we were initializing this S0 previously? Whenever we are just dealing with the RNN, how we were initializing that S0? S1 depends on S0, S2 which depends on S1, and so on, right? Not only S1 but input also. But S0, that is the initial value, we were generally initializing with the help of some random numbers, right? So that would be random initialization. But now, in this case, what we are doing, instead of initializing that S0 with some random number, what we'll do, that S0 will be the output of the CNN. So from this image, you can say the output FC7 is something which is learned by the machine, or you can say that is something which represent this particular image. Yeah, it's a vector. Fine. So if I feed this RNN with the output of CNN, what happens? Can I say that this subsequent calculation, that is S1, S2, S3 up to Sn, all this computation are dependent on the CNN with more or less impact of that particular CNN architecture, right? Fine. So this is the first approach, the first way to feed the output of the CNN to your RNN network. Another approach is, instead of feeding it to the S0 only, what you can do, you can feed it to all the entries. Along with the input, what I can do, I can feed the CNN output at every layer, at every input. Fine. So at any layer or any timestamp t, the value of st is RNN of st minus 1 xt, that is input, and this FC7. Right, so we'll apply that RNN operation on this 3 combination. Previously we were just applying it on 2, input and ST-1. But now we are combining it with the CNN output also, that is FC7 output also. And so this is another way to feed this particular CNN's output to your RNN model. Are we fine up to this? Any doubt in any of the option 1 or option 2? In option 1, we were just feeding it to the first, that is S0, first state. But now in the option 2, we are feeding that particular FC7 to all the state. That means at all timestamp, along with input, along with the previous state, we are also feeding the CNN output. Fine. So the discussion that we have done, that is nothing but the encoder-decoder architecture, where the CNN, you can say that's the encoder, which encode the information that you have, the name, the reason behind that name, which encode the information that you have. So in our case, the information is the image, which is encoded in some number, right? So that is whenever we are fetching that output FC7. Now we will feed that encoder output to a decoder. Fine. So in our case, the encoder is CNN, the decoder is RNN, but depend on the application, you will have different combination of this. We'll see some of the application. So where you will easily identify what should be the encoder, what should be the decoder, and how should we connect that. Fine. And we have seen two different ways to feed this encoder output to the decoder. The first way is just feed it at the beginning. The second way is feed it at every timestamp. Fine. And this both encoder and decoder can be any kind of neural network. It can be CNN, it can be RNN. Sometimes you can also use the feed forward neural network. Make sense? Just try to imagine the current scenario, current application requirement, where you have some image and you need to generate the text related to that image. Fine. So far, whichever algorithm that you have learned, no matter whether it is pure neural network or any machine learning algorithm, or even if it is a deep learning architecture, let's say CNN or the RNN, none of them can able to handle this kind of application. Why? Because to handle that image, we need to deal with the architecture something similar to the CNN. To deal with the text data, which is we can say to deal with the sequential data, we need to deal with some recurrent network, that is the RNN network. Right? So if I just use either CNN or RNN, this purpose can't be solved. So you need to combine the two models somehow, and that combination is nothing but this encoder decoder architecture, where at the encoder layer, whichever information that we have, we are converting or we are encoding that information into some vector, into some matrix form. Right? Then we will feed that encoding information to the next architecture along with some other input, and that next architecture will decode it and it will generate some other output. So that other output generation is dependent on the input that we have provided to the second decoder, as well as it also depends on the encoder. And encoder eventually depends on your another input. So we can summarize this full architecture as the output generated by decoder depends on both the data, that is this input text as well as the image. Fine, so dependent on both, and that's what we want. Fine, so this is the main heart of this encoder decoder architecture. Fine, so there are some advancement in this encoder decoder architecture, that is referred as the attention based mechanism. But are we clear with the plain encoder decoder? Any doubt in this encoder decoder? we have seen two ways, right? So there are actually many ways, but out of that many way, we have seen two simplest way, where we may feed it to the initial timestamp or we may feed it to all timestamp. Specifically, whenever your decoder is RNN and the encoder is CNN, right? But you can have different combination. Fine. So this is the architecture that we have used. The CNN encodes the image. Whatever that encoding result, that will feed to RNN, which is decoder, right? And there are two ways to feeding. One is we can just feed it to the first value, which is indicated by this first arrow, right? And another way is we can feed it to all the timestamp, which is indicated by this dashed line. Yes, good question. So what should be the other input except image? Okay, to answer this question, can anybody tell me whether this is supervised model or it's unsupervised model? It's a supervised model, so right? So we need to train it. So let's say for the current application or the current requirement where we need to generate the caption for an image, initially during the training phase, what you need to do, you need to provide image as well as caption for that image. That image will give to the encoder part and the caption will give to the decoder part. Right? That is over here. Right? So that will be the training phase. Now during the testing phase, what we'll have, we just have this image as an input. Fine. So now to provide this second input, that is the text input, what we can do, we can initialize it with some ghost symbol or you can say the start symbol. Then based on that start symbol and the image, once the RNN is applied, we'll get some output. Let's say that output is A. So now for the second timestamp, we'll feed that text along with the image. And so once again, this RNN have a text information, it have the image information, and it will generate the next word. Let's say man. Next, we'll feed it to the next layer, the next timestamp, and so on. Right? So this is at the time of testing, but at the time of training, what we need to do, we need to feed both the information, caption as well as the image. Fine. So machine will learn how to generate the particular caption with respect to a particular image. Fine. And as it's an deep learning based model, your training size must be very, very, very large. Fine. Muktan? Okay. Right. So for different architecture, we need to identify what should be the encoder and what should be the decoder. For one application, we have just identified that is image captioning. Fine. So now let's say if some of you may wants to work on this image captioning, what you need to download the latest paper from the Google Scholar or from some reputed journals. Fine. So if you refer that paper, majority of them must have used this encoder decoder architecture with some modification. And so whenever you refer a particular paper, what you need to do, you must clear with this encoder decoder. So now once you are clear with the encoder decoder, from the paper, what you need to find, what is the difference than the normal vanilla encoder decoder architecture, which additional thing or which additional stuff they have done so their performance is improved compared to the previous result or compared to the previous state of art results. Fine. But for that, you must clear with this encoder decoder, and the majority of this application will have this architecture, right? So rarely you will find the paper where some other architecture is used. Otherwise, it is based on the attention. Sorry, it is based on the encoder decoder itself, right? And this is just the base, or you can say vanilla version. There are many different variants of this encoder decoder, but this overall phenomena should be clear in your mind. And so we'll now next see different application. For that application, what should be the best encoder, what should be the best decoder, as well as what should be the parameter, and how we'll design our loss function. So for our application, which is image captioning, the data set is image, that are the x value, and y, that is caption, right? So initially we'll feed this x and y both during the training phase, fine, so that you can identify how accurate this performance, fine, how accurate the result which is generated by this particular architecture. And our encoder is CNN, decoder is RNN, fine, and the final output would be the softmax on the full vocabulary. And then think about the size of that softmax also, right? You have all the words over there, and that's why if you can recall the stemming operation, right? I guess last to last lab, Devang might have encountered that we should reduce the size. The stemming, the usefulness of the stemming is to reduce the size of vocabulary, and which is very essential whenever you are dealing with this kind of model, because whenever you consider the softmax, it deals with all the vocabulary words, right? And it will have probability value for all of them. And from that, we need to pick the highest probability word. Fine. So the algorithm would be the gradient descent with the backpropagation, and the loss function will be our log loss, or the gross entropy loss, right? Another interesting application that you can use is this textual entailment, sorry, where you have some input. Let's say the input is it is raining outside, and the output that you need to generate is, let's say, the ground is wet. Fine. So depend on this. Let's say if I say this is statement A, and let's say this is statement B. So you need to generate this statement B such that it satisfies this statement A, right? And it should be some different statement than this A. Fine. So now, which kind of architecture we need to use as encoder as well as for the decoder? Both should be the RNN, right? So now the interesting point is, if you use both value as an RNN, then how you will feed something over here? Because if you consider the RNN, we have output at every timestamp. So interestingly, observe this particular scenario, the encoder part, where we just have two entries. This is state. This orange part is your input, right? And from this state, we are not interested to generate the output. Right? We are just interested to complete the statement. Once the statement is completed, whatever is the final output, that is at the timestamp t, whatever is the output, that we will feed to the next RNN model. Makes sense? In the case of RNN, we have seen two variants. In the first variant, we have observed that at every timestamp, we are interested to see what is output, as well as we'll feed it to the next timestamp. And we have also seen the another architecture where we are interested to see the output at the end only, right? No matter whatever is output at intermediate timestamp, we are not interested in that. We'll just fetch the output from the final state only, right? So you need to use that version of the RNN over here in an encoder. Right? While in the case of decoder, we need that value uh, at every timestamp. Well, we'll not just feed the outside. but actually this output, you can say, it encode the information of all this data. It is raining outside, because we are not just only feeding this outside, right? So we are not feeding that x4, but what will feed this output ht. Fine. So if you see that ht, it is not only depend on the outside, it depends on this previous value also, the previous timestamp, the state value.
to identify, so many algorithms are there to identify the symbols. Advanced level algorithms will be needed from your image to identify frequently occurring symbols. But right now, what we have assumed uh, that these symbols are known to us, that these symbols are occurring, or manual input or some automated input. That is not our concern right now. Our concern is symbols are available with us. If so, then how we can compare? Okay. So otherwise you can give the manual inputs, that's fine, or you can have automated some algorithms which are possible. But right now we will not study them. Right. So so that is fine. So we had it. So we had three symbols which are frequently occurring. Now how to compress? So you will see where exactly for, symbol 0 occurs. So for that XY location, you will show that XY location. Assuming my index starts from 0, so this is 0, 0 location. Where exactly B starts, so you can see this point starts here. What is that location? It is 0, 2. This is 0, 0, 0, 1, 0, 2. So at 0, 2, symbol 0 occurs. Yes or no? Then where this symbol occurs, if you will see where this symbol occurs, this location, you can see this location, where this symbol occurs. So that location you are going to give. What is that? If it is 0, 1, 2, 3. So this is 3. And horizontal, if you will check 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, and 10. So that occurs at 310. It occurs at 310. What occurs? That symbol 1 occurs. Same way, whatever the coordinate here, you can see that this symbol occurs where? So that occurs from here. That coordinate you will identify, that will be 318. The width will be 18, and from here you can see that 0, 1, 2, 3. So 318, symbol 2 occurs. Then again at this location, which symbol occurs? First symbol occurs. First symbol is of A. That XY coordinates are 326. This is 326. Same way, this is at 334, again 2 occurs. Again at this location, if you will see this location, this 342, and at 342, 1 occurs. So what we will send to our receiver, or what we will store, we will send this dictionary, and we will send this. So you may ask, okay, but will it compress because we are sending this information as well? Will it compress? So that we have to calculate first. How many bits I am sending now? 9 into 7 plus 6 into 7 plus 6 into 6 plus 1 byte for this, 1 byte for this, 1 byte for this. So 3 bytes, the 24 bits here, 24 bits for this, 24 bits for this, because 1 can be represented by 8 bits, right? So 8 bits, 8 bit, 8 bits, 24. Again next 24, next 24, next 24. How many times? 1, 2, 3, 4, 5, 6. So 6 into 24 bits for this, and 9 into 7 plus 6 into 7 plus 6 into 6 for this, plus this many bits we are transmitting. Earlier, how many we were transmitting? So we can say that 1, 2, 3, 4, or we are sending an entire image. We were sending this entire image. So they were 1, 2, 3, 4, 5, 6, 7, 8, 9 pixel in height, and width you can calculate 1, 2, 3. In that way, if you will calculate whatever the height is, right, or width is, so that width is 51. So earlier we were sending 9 pixel, 9 into 51 pixel, and 9 into 51 bits. Here they were just 1 and 0. Wait, here this grid is of size 9 into 51. This grid is of size 9 into 51. Assuming that if they are made up of 8 bits, then you can send it like here 8. But if you are assuming it is a black and white, so what will be the size here? It will be just 9 into 51 bits. Suppose we are sending 8 bits, it will be 9 into 51 into 8. But just one pixel, one and 0, only two values. So you can have 9 into 51 into 1. So that will be the size that you are transmitting, and there were 459 bits. We will have 459 bits. Okay. And here if you will see, here assuming this is made up of just one bit, 1 or 0. So here 9 into 7 bits, 6 into 7 bits, because each square is represented by 1 bit only. So 9 into 7 bits plus 6 into 7 plus 6 into 6 bits, that many bits are needed. Plus how many others? 6 into 3, so 6 into 24, that is 6 into 3 into 8. 6 times is into 3, and for each 8 bits, right? So what is the compression ratio? So total number of bits will be 285. Earlier were 459, and the compression ratio will be 1.61. Okay, so are you clear with what is symbol based coding? These two examples by mistake they came here. This is symbol based coding, and its example is here. Any doubt in this coding example? So it is compressing. It is compressing by factor 2. It is compressing almost by factor 2. But this methodology will be difficult because we have to recognize the symbol frequently, exactly occurring symbol. Synthesize images can have this, but otherwise it is going to create problem, right? So that was all about symbol based coding. Now next is bit plane coding. What is bit plane coding? See, for run length, if you remember, suppose it is my black and white image, na? Run length will be more powerful. Why so? For black and white image, because only two intensities are there, so there will be long run of zeros and long run of ones. If we are frequently occurring intensities are there, then run length coding can be less effective, because similar looking intensities like to 126 and 127 are similarly looking intensities, but they are not same. So run length coding will need 2 bits for each. So if it is black and white image, it will be more effective. Same way symbol based coding we have seen for black and white, right? So if I in my image, if I can convert my image into black and white and still can preserve the information of intensity, then impression can be even more impactful. What I will do, I will convert my image into black and white first, and then I will code it using run length or symbol based, and then when I will decompress at that time, I will regenerate my intensities as well. But if I am using thresholding, that any intensity above threshold will be white, any intensity below threshold will be black, then you will never be able to go back to your original intensity. So this is not a good way to convert it into black and white. Another way of converting that into black and white images is bit plane. Convert it into bit planes. Assume that your intensity is made up of bit multiplied with 2 raised to weight of 2, like 2 raised to 0 plus 2 raised to 1 up to 2 raised to 7. Assume that it is made up of bit uh, uh, multiplied with weight of power of 2. And if you remember, we had LSB bit, we considered all LSB bits, then we second bit took, then we took third bit, and then we reached to MSB bit. So now if you remember, this was also black and white. So now these images are black and white, so you can effectively apply run length coding to them, you can compress them, and you can send it. At the receiver, what will happen, or while retrieving, what will happen, you can decompress and you can reconstruct the image from it, and it will use the run length coding or symbol based coding effectively, plus it will preserve your intensity information. So that is what is known as bit plane coding. Okay. So this you know already. If my image is having 1000 value, how it is equivalent to which decimal value? So you can say this is multiplied with 2 raised to 0, this is multiplied with 2 raised to 1, this is multiplied with 2 raised to 2. So bit value, A value is the bit value multiplied with some power of 2. And that is what is this. This is how you can get the equivalent intensity value. Yeah? Okay. But now there is a problem with bit plane slicing. What it is? Suppose in my image intensity is occurring like 127, 128, 127, 128. Visually, will this patch have difference? Will you be able to? How you will look this? You will look it as constant gray region of 128 intensity around, because you cannot differentiate between 127 intensity and 128 intensity. So for you, it is a constant patch. but it is having these two intensities. So now what you will do? So now your 8-bit plane will be like this. 0, 8-bit plane, you understand? So it is 0, then 1, 0. That is MSB I am extracting from all. Then 1, 0, 1, 0, 1, 0. Right? 127 is 0, 1, 1, 1, 1, 1, 1, 1. This is 127. And 128 is 1, 0, 0, all zeros. Right? So what is my MSB? MSB will be like wherever 127 occurs, it is replaced with 0. Wherever 128 occurs, it will be replaced with 1. So this is my MSB. Same way for LSB, wherever 127 occurs, it will be replaced with 1. Wherever 128 occurs, that will be replaced with 0. And if you will go for intermediate values, this will be your bit plane. And apply run length coding now. You cannot apply run length coding here. Why? Because 0 occurs 1, 1 occurs 1, 0 occurs 1, 1 occurs 1. So run length coding cannot be applied if it is having alternate values. Actually, it is having constant patch. But this is the problem with bit plane slicing. Here you cannot apply because alternate anywhere in none of the bit plane you can apply it now. In the none of the bit plane. So no meaning of compression. Here you are expanding the size if you are using the solution that we just discussed. So what is the solution of this problem? Solution of this problem is gray codes. Don't use binary codes, use gray codes. What is gray code? Gray code is first MSB will be kept as it is. Next bit will be XOR of this two, that is 1. Next will be XOR of this two, that is 0. And next will be XOR of this two, that is next will be the XOR of this two, and this two. You know that very well, how to convert into grayscale. So this is gray codes. Instead of binary code, this is the gray code. And for 127, if you will go for, then this will be gray code. Okay. So what is the property of the gray code? Consecutive numbers vary by at most 1 digit. The consecutive digits are varying at most by 1 digit. Other digits are same. So now instead of converting this into bit planes, I am converting this into bit planes. Gray code binary planes I am constructing. Okay, so what will be my 8-bit plane? Wherever 128 is, I will replace it with 1. Wherever 127 is, I will replace it with 0. So here it will be 0, 1, 0, 1, so on. So you will say how it is different from this. It is not any way different from this. I agree. But what about next one? Wherever 128 is there, replace it with 1. Wherever 127 is there, replace it with 1. So wherever 127 is there, you replace it with 1. Wherever 127 or 8 are there, they are replaced with 1. Same way for other the locations you will see, they are replaced with 0. Both of them are replaced with 0. So now these are my bit planes. And here I can apply run length coding. Here I can apply my run length coding. Here also I can apply my run length coding. Only this will create the problem. Okay. So that is what the methodology is. What is the idea? That convert into bit planes so that now my grayscale is now binary and I can apply run length coding here and it will give us the effective idea, effective way to handle it, right? But the problem is if this type of intensity change occurs, then consecutive 1010 will not take place, alternate 1010 will take place, and hence decoding is, I mean, compression is not possible by this. The solution is use gray code. So now if suppose this is actually made, and if uh, uh, the if because my if it is 7th bit plane or MSB bit plane is taken, it is this as it is because it is same for binary bit plane and gray code bit plane. But now here if you will see, this is my binary 6th plane and this is my gray code 6th plane, and you can see the alternate ones and zeros are reduced here. Alternate ones and zeros are reduced here. All they are consecutive ones. They are consecutive ones. So here more compression is possible. Here also you can see. This is the result of 6th bit plane of gray code and this is the result of 6th bit plane of binary code. Same thing is true here as well. Same alternate values are reduced here. Consecutive values having same values are more compared to 5th plane even. You can check it in 4th plane and so on. And this is how it will help. Okay. More discussion on predictive coding will be taken in next lecture. Any doubts so far? Comfortable with bitplane coding and symbol based coding? Okay, so we will discuss further in the next lecture based on we will discuss predictive coding in the next lecture.
So, good afternoon, everyone. Am I audible to everyone? Okay. So, all of you are getting my CentOS now? Okay. Fine. So, let's start from where we left in the last class. So, we were talking about Spark SQL, and we started it in, we saw some theory, and then we started demonstration also. We started it in local mode. There was a problem with standalone. I have identified the problem, right? So, let's proceed with standalone mode now. Now, to start Spark in standalone mode, what I need is Spark's cluster manager or resource manager. So to do so, what I'll be doing is start master.sh. It should start my master daemon. So that has been started. To start slave, I was making a mistake in starting this slave. So it should be start slave.sh, and then immediately I have to specify spark colon double slash Hadoop master colon 7077. So the worker is started, right? So what mistake I was doing? Anyone could identify? Last lecture, what was the difference? Master, right? So hyphen master I was specifying, and that was not needed here, right? So because I had a practice of specifying master when starting Python shell or Scala shell, right? I by mistake typed it here also, and that was the problem, right? So otherwise it starts, there is no any other reason for it not being started, right? So our master and worker daemon has been started. So this means that your cluster manager is now ready and executor is also now ready. Let me just start my HDFS, because I'm going to show you how we can interact with HDFS too, right? And standalone mode. So I'll be simply starting HDFS, and let me just start Firefox so that we can see the GUI part as well. So I should be able to see all those three daemons related to HDFS, right? If everything has gone fine. So I've got it, right? Name node, secondary name node, and my data node, right? So these are three daemons that has been started because of this start DFS command, right? Now let me just show you what is there on my HDFS. So do you see this partitioner demo folder, inside which I have input folder, inside which I have partitioner input.txt file. I'm going to read this file and I'm going to process it in Spark, right? I hope all of you are following what is going on here. Everyone is with me. We have started a Spark in standalone mode, and we are going to use HDFS as a storage from which I'm going to access a file, right? And I'm going to do analytics using Spark now, right? And that to Spark SQL, let's say, right? So what I have to do now is I'll be starting my PySpark, that is Python shell, right? Here I have to specify master, right? So Spark Hadoop master. So the Python shell is ready, right? So if you want to launch or if you want to work with Spark SQL, what is the first thing that we do? PySpark dot SQL import Spark session, right? I don't need it right now, just showing you for you only, so that if you are writing it in Python file, you have to include this file, right? Then next thing is Spark is equal to Spark session dot builder dot app name. Let's say I'm giving name basics only, dot get or get, right? And then what I'll be doing is df is equal to spark dot read dot csv, and then here I have to specify that path. So my path is partitioner demo slash input slash partitioner underscore input dot csv file, which I just now showed you, right? So now if you there is a problem in path itself, right? Otherwise it will read for sure. Let me just confirm this. It's partitioner demo slash input slash partitioner underscore input file. Okay, it's txt file here. And then there is a problem. Yes, so now it has read it. So it was not a .csv file, it was .txt file. So now you have got your data frame available, right? Now if you see df.show, it should print, right? This was our data. If you say all those things that we did in the last class, you will see that they are applicable here. Describe if you do, right? It would describe also, right? You can also say df dot print schema, right? So that would print schema also. You can say df dot head and to, right? So this would, you can see the row object is returned, right? So the first line and the second line, two row objects are returned here, right? So this is what we have done just now is we have started Spark in standalone mode. Then we have started HDFS daemons. For storage, we are using HDFS daemons, right? So from Spark, we accessed that file and then we have created a data frame and we are doing Spark SQL on it, right? So now, as I said in the last class, by default, Spark automatically tries to infer schema from the file, right? But if there is a need to have specific schema, then we'll have to specify it explicitly, right? And in this case, if you specify schema explicitly, by some way, Spark will not automatically infer schema. Instead, it will only read the created schema and will try to fit the data to the schema that you have specified, right? So this is one more thing for your reference. You can create your own schema too, right? Now, how to do so? So there is something called as struct type available, which is used for doing this. So what you have to do for this is from pyspark.sql.types, you have to import struct field, comma, string type, comma, integer type, comma, struct type. Let's say I'm importing these things, right? Then I'm specifying a schema. So what is going to be my schema? So my schema is equal to struct field, right? Inside I'm specifying first field is ID, whose type is going to be integer. So it is integer type and true, nullable true, right? Then another one is a struct field. The second one is, let's say, title, string type, and true again. Then the next one is, let's say, again, struct field, author, and this is also string type, and this is true, right? And then the last one is also struct field, format. This is also string type, comma, true. And now the last one, struct field, price. Let's say I'm taking integer type. And then I say true. Right? So, okay, integer type, I have not specified. There is spelling mistake somewhere. Okay, here. I'm doing a lot of spelling mistakes, right? I mean typing mistakes. Okay, now it's okay. So my schema is created, and then what I'll be doing is my final schema. This is just a way to have your own schema. I'm just showing you one way, right? There is one more way, but this one is more simpler one, right? Struct type. Then I say fields is equal to the schema that I've just created. I'll explain you everything soon, right? So this one is created. Now what I am doing is df is equal to spark dot read dot csv, and I'm going to read that book list file where these fields are there. If you remember, we read this file in the last class. It's available in downloads and book list dot csv. Now, if I do so and complete my bracket, it would infer schema. But I wanted to use my schema. So what I'll do is schema is equal to final struct. Right? So I'm saying Spark to please use my schema. Now, if you see here, you can see that it has used my schema, right? So let me just explain you what I have done just now. Let me show you the file first of all. So this is the CSV file that we are reading, and you can see it has got these many fields. These are its fields, right? So if I don't specify schema, of course, Spark was taking schema appropriately only, but it was giving some different column names. Now I want to use this column names only, right? And I, let's say, want to use integer here only in case of price, and I don't want to go for float value. So let's say these are my restrictions. So I have used my own schema here. So using a type, you can do so. So what we did first is import struct field, and then string type, integer type, and struct type. So this has to be imported. Next thing is you have to define your schema. Now what attributes are there in your own file that we have specified here. So you can see I have taken ID as integer, title as string, author as string, format as a string, and price as integer. So this is my schema that I have specified, right? Then what I'm saying is final underscore struct is equal to struct type fields is equal to what I specified in data underscore schema. So this structure is created, right? This schema is created, and this is what we are going to specify here. So the file that is specified by this path will be read, and it will be read to fit to the schema that we have specified now, right? Now you must be knowing that if I don't specify this thing, if I don't specify this thing, right? Let's say I'm creating another data frame, right? Now, if I say df1 dot print schema, what it will print? See, are you able to see the difference? Yes or no? All of you are able to see the difference here? So in the previous case, as can be seen, it has taken my schema, whereas here it is using its own schema. So though it has identified columns properly, right, it is taking everything as a string, and it is using its own name and all, right? But now I have enforced it to use my schema, right? So that also can be done very easily. Right now, once your schema is created, or once your data frame is there, right, you can perform a lot of other things, like let's say if I do this, right, it will show me that it's a column. If I, let's say, do this type of df id, right? You can say it will tell me that it's SQL column, right? If I say df dot select id dot show, sorry, so it is simply showing me ID information only. I can specify any other column too, right? So another thing is if I do so with column, right? And let's say I say new ID now, right? And I am just renaming a column actually, right? Please remember this is just done in temporary storage. Actual data frame is always immutable. So it will not change for sure. But you can see I've added, not renaming actually, I've added a new column here, which is a new ID and which is very similar to the original ID column. Right now, this means that I can perform any other operation like what I can do is, let's say, double. If this would have been age and I just want to double the age, right, then I can simply do this, right? So you can see it is multiplied. So any other operations also can be applied, right? You can also rename it with column renamed, id as, let's say, make id, and then I would say show, right? So you can see the name of the id column is changed, right? But again, if you do so, df.show, you can see the original thing cannot be changed, right? This is just for display purpose. In temporary storage, it might be doing a change. So originally data frames are immutable like RDDs only, right? So these are some SQL operations that can be done, right? We can also perform something like, let's say, df dot create or replace stem view. Let's say I'm saying book, right? And then I can say SQL underscore results is equal to spark dot SQL, and then let me just say select star from book, right? And then I would say SQL underscore results dot show. So you can see I've written SQL query on a data frame, right? And then you can write any other query here, right? So we can write queries and we can retrieve results also. So that is all kicks to Spark, right? You should be able to install and you should be able to run anything in your machines. Right now, in the last class, I told every one of you to be ready with your infrastructure. We'll be going with Spark